a kid runs at a merry-go-round. We talked about this yesterday, right? Jumps on the merry-go-round. When done, kid and merry-go-round are spinning. Can you guys, is that something that you can reasonably think of in your head? Okay. So let's consider there's two parts to this, and there's a part in the middle that we're not talking about that we'll need to. Because there's a kid running at the merry-go-round, and then there's the future issue where the kid is on the merry-go-round. Well, how'd that work? The kid is on the merry-go-round, and the kid and the merry-go-round are spinning. This particular kind of collision does not conserve linear momentum because of what's not talked about, the part in the middle where the kid is landing on the merry-go-round. And that's the part that we need to kind of talk about, because in this class, unlike in mechanics, you have to be able to explain what's happening and use your physics words, all of them, to talk about what's happening. So I want to talk about that moment when the kid touches the merry-go-round, when their foot slams down against the merry-go-round. So right here. So at this instant of contact, the kid is still moving this way because their foot is just starting to hit the side of that merry-go-round, but the merry-go-round has not started moving. Do you remember how we would talk about this with like a regular linear collision? And we talk about that moment of contact. So a collision, even in these examples, is the instantaneous moment before contact and the instantaneous moment after contact. That's a collision. So although the kid might be starting off pretty far away from the merry-go-round, that's not really part of the collision. The part of the collision that matters is the instant they are jumping onto the merry-go-round. At that moment, they are applying a force to the merry-go-round, and the force they're applying to the merry-go-round is in that direction, right at the very edge. At the same time, the merry-go-round is applying a force to them. Between the two, those two forces cancel out. And if there are no other forces in the system, then I would expect the merry-go-round to start moving this way. Like it would drift that direction. Like if this whole thing was on a frictionless surface and the kid just jumped on the merry-go-round. Say it was a round piece of ice floating on another piece of ice. I mean, make up something, but you get the mental picture. The whole thing would start to move. But this is at a playground. So we know that there's an external force on the system from the ground on the merry-go-round to keep the merry-go-round from moving. Sound okay? All right. That means that linear momentum is not conserved in this kind of collision. And that's because there's a fixed pivot point. Put that in your notes. That's the reason why linear momentum is not conserved, because there is a fixed pivot point. It is being held in place. That is why. And you need that. You need that as part of your explanation. Why isn't linear momentum conserved? That is why. Again, it's because it has a fixed pivot point. It's being held in place at the point where it pivots. I'm saying all those words because they're important for what I'm going to say next. You see, in this collision, although it's a fixed pivot point, we know that after the collision, the system's going to start spinning. We know that's going to happen. So there must be something about the kid's motion that could be used to help us predict what happens to the merry-go-round. And what we say is that the kid, although has linear momentum before the collision, we also say that the kid has angular momentum relative to the merry-go-round. These are two statements that you need to kind of appreciate. They're not necessarily directly related. I mean, obviously, I'm telling you from the beginning that linear momentum is not going to be conserved because there's an external force. But the kid also has angular momentum relative to the merry-go-round. Now, this is a weird concept because it looks like the kid's just running in a straight line. It doesn't look like they're spinning. Would you agree? They look like they're just running in a straight line. So it's kind of weird to say, how do you mean they have linear momentum? It's in the way I talk about it. They have angular momentum relative to the merry-go-round. So imagine you're standing at the center of the merry-go-round. So you're standing right there. And you're watching this kid, okay? You guys get an idea? You're standing at the merry-go-round watching this kid. Let's say the kid misses the merry-go-round, okay? Jumps but misses and just keeps going. Wouldn't your head kind of do that as you watch them? Now, pay attention. Right? You see how you'd have to swivel your head to watch the kid run by? What we say is that from the standpoint of the merry-go-round, the kid is spinning around the merry-go-round, even though they're just going in a straight line. For the instant that they're coming towards the merry-go-round and passing the merry-go-round, they are sweeping out a vector that rotates around the pivot point. They're also getting closer and then getting further. That's also happening. But from the vantage point of the pivot of the merry-go-round, they are rotating about the pivot point, even though they're going in a straight line. I know it seems weird, and I'm going to do math in a minute, and that might even make it weirder, okay? So for a minute, let's just look at math. I like math. I know you guys are scared of math. I like math. You know why I like math? There's no exceptions, right? The rules are the rules. I want to talk about this particular problem in the vantage point of just simple rules. This line represents the path the kid runs along. Is that okay? Does it look like it's nice and tangent to the merry-go-round? I'm just going to talk about the approach. The center of the merry-go-round is right here at its middle, and the kid is running towards the merry-go-round. I want to consider these spots where the kid is running. At the very beginning, if I draw this arrow represents the vector from the pivot point to where the kid is running. Is that okay? And the kid has a velocity in this direction. So they have a linear momentum of mv. And this long arrow is a vector that connects the pivot point to the guy. It's a torque arm that connects the pivot point to the guy. Is that okay? Now, after a few moments, would you agree that they've now run to here? Of course, if they're just running and they're keeping themselves at a nice, even pace, they still have the same momentum. Still okay? They run a little further. So now they're here, but they're still running, so same momentum here. And eventually they make it to here. Now you see that R is getting smaller all the time, right? As it gets closer, but do you see how the R is sweeping this way until eventually we reach this point right here, which is it's like the radius of the ride, but it's as close as the kid gets to the pivot point. Do you guys see that? It'll never get any closer. We call this the point of closest approach. And it's when R is perpendicular to their momentum. It occurs at a special spot right there. The point of closest approach. See, here's the thing. We say that the kid has angular momentum relative to the merry-go-round. Now, we know that angular momentum is I times omega. Right? We know that. We've talked about that before. Okay, here's where it's going to get a little bit weird. Are you okay to kind of follow along with me for a minute? Imagine for an instant that at this instant, right here, okay, that they're going even though they're going in a straight line, for one instant, V equals omega times R. For that instant. That would be how fast this arrow is moving. That'd be the omega for the arrow. You follow that okay? It's a little weird, but for that instant it is. But R is changing. So R gets shorter and the kid stays at the same speed. So it looks like omega's different as the kid moves. Because like over here, R is shorter. So this V equals omega times R will be different, suggesting that omega keeps changing because R keeps changing. You follow me so far? But I just want to hold on to that thought for just a minute, because if we look at this L, we could write this as I times V over R. I know this is going to be weird. Just keep going. They're a point mass, right? Point mass has a moment of inertia of mx squared. But they're a distance r away, so the x becomes r for that instant. I know r keeps moving, but for that instant, x becomes r. So this becomes mr squared times v over r. If I mash this around, I get r times mv. Now, I'm showing you this even though it's unnecessary to understand the topic. I'm showing you where something comes from. Because what we actually say is that, and we use a lowercase l for this, is that a point particle has angular momentum relative to a pivot point. This only makes sense in the context of a problem like this. But what we say is a point particle has angular momentum relative to a pivot point. Again, this only makes sense in a problem like this, where the rotational motion of an object is related to the linear motion of an object. So this kid running at the merry-go-round is going to cause the merry-go-round to spin. It'd be similar if you were swinging a baseball bat and hitting a ball. The swinging of the bat is angular motion, but the motion of the ball is linear motion. But we can explain what's happening if we say the ball has angular momentum. So that's what this is all about. It's only in service to problems like this. It makes no sense to say that a particle just traveling in a straight line has angular momentum. It requires that there be some reason. And in this case, the reason is that we're going to pivot about this point here. So there has to be a context. So just random things moving in a straight line don't have angular momentum. This has angular momentum because the kid's going to jump on the merry-go-round. And we define that angular momentum, and you're not going to like this, because although this is where it comes from, I never talked about the angle involved here. So I have to add something. It's r times mv times the sine of the angle between r and mv. Meaning because that r keeps changing and because it's at a crazy angle, this angle matters. Now, that's the definition of the moment of inertia of a point particle. And I'm going to tell you right away that unless the problem is trying to be weird or trying to just see if you know this particular definition, we in this class will never use this in a collision. Okay? There's a shortcut, and the shortcut's important. In fact, the shortcut is more important than that equation. And I want to show you the shortcut. This is going to involve more math. Are you okay? I want you to look at these pictures I've drawn. I didn't draw them accidentally. I want to take issue with this. I never want to use this again. I want to use easy stuff. Remember how we try really hard to make our angles 0 or 90 all the time? Because the sine of 0 is 0 and the sine of 90 is 1? I want to try and do that here. Is that okay with you guys? The kid's going to run and jump on the merry-go-round. We know that. Eventually, there is a moment over here where the angle is 90 degrees. What I want to prove to you is that no matter where they are here, although this angle is changing and r is changing, I want to prove to you that you can always just say r perpendicular mv and ignore the angle. I want to prove that that's true. that their angular momentum is a constant, even though r and the angle are changing. Are you ready for the proof? Okay, the proof is easy. We're going to look at some triangles. Triangle number 1. Triangle number 2. Triangle number 3. Do you see how each triangle goes to where I put those little stop markers? Here is the angle for the first triangle. The sine of that angle would be opposite divided by hypotenuse. We'll call that R1. And this is angle 1, the yellow angle. Okay? Let's look at the blue angle. I'm sorry, let's look at the green angle. I'll make this one green. The green angle. That's angle 2. The sine of angle 2 will be R2 and R perpendicular. Do you see that too? Now, there's another angle. We'll call this the red angle. This is 3 and this is R3. Do you see that the sine of that third angle is equal to R perpendicular over R3? Is it clear where I'm going with this? That if I multiply all of the bottom numbers, they all equal R perpendicular? So this and this always work out to be just R perpendicular. Always.